Yeah, no.
We have a 30-day week. That's so nice.
You don't know how to do it.
Could have been late. Hey.
No, he's gonna change.
Yeah, you're supposed to go if you're excited. Or no, what? You're just projecting these. Yeah, yeah.
And then you can
Well, there was like
only seen it.
but she didn't cover.
No, they call it.
Like,
Once on social.
she was like,
To punch the benches.
"Wait," and I was like,
Even though
I
it's.
think so. Yeah. No, it was not why the. I mean, they.
It's just weird, like. Yeah, for that. That's like
Okay, if you guys can have your calculators out, as we're gonna start unit 9. So, overall, I think, unit 9 is not too bad. I think a lot of, what you're gonna see is just going to feel like an extension from what you've seen with derivatives and integrals. I think the one thing that, is probably gonna give us a bit more trouble is polar area. So we're definitely gonna spend a lot more time when we get to polar area. It's just, the way that area is found is different than what you would expect from a rectangular graph. So that will take some time to get used to, but we'll definitely spend a good amount of time trying to get more comfortable with that. But if you look at the calendar here, we're not going to get to polar area until until closer to the end of next week. So today I'm just going to introduce parametric equations. Tomorrow is your quiz, unit 6 to 8. You guys picked up morning review worksheet. So this morning I went over the morning review worksheet 1. The key is attached as well. So I encourage you guys to work through worksheet 1 just for extra practice. And I recorded a video as well, so I'll upload that under today's date. And then tomorrow morning, help session at 7:30, and I will work through worksheet 2 as well as any other additional questions that you may have. Also, at the in your quiz review packets, you guys have that worksheet 1 through 3. A good thing to look through is also the end of that worksheet 1, formulas that you want to make sure that you're familiar and comfortable with going into the quiz. So tomorrow's quiz, you get to have a calculator, but I'm going to ask you to show your work. Like I said, if you didn't have a calculator, so if you're just entering in a definite integral problem without showing work, that's not going to be able to earn you full credit. So you can have a calculator to double check anything that you want to double check, but to earn credit, I need to see all your work. Right? Any questions about tomorrow's quiz? Right? Okay, so we've been looking at graphs of one equation with 2 variables, typically x and y. And now we're going to look at the third variable that will represent a curve in the plane. So in the rectangular equation, you are able to determine where the object is located. But with the addition of the third variable, often it's going to be variable t for time. We're able to determine when the object was at that point. And the third variable is often time, but not always. But for us, it'll pretty much always be time. So parametric equations, if f and g are continuous functions of t on an interval, then the equation x equals f of t and y equals g of t are parametric equations and t is the parameter. You can sketch the curve of a parametric equation by substituting in values for t. Number one is to sketch the curve with the following parametrics. We have x is 2t, y is defined as t squared minus 1 between -1 and 2. So I'm just going to plug in -1. So we're going to start at t equals -1 and figure out where the order pair is. At -1/2, we'll figure out where the order pair is, and then we'll connect those dots, and it's going to create a curve that we'll probably be able to recognize. So if I plug -1 in for t to find x, I'm going to get -2. I plug -1 in for t to solve for y, I'll get 1 squared minus 1, which is 0. And I'm going to plot that point here as well. -2, 0 is my order pair. All right, next up, -1/2 in for x for t to solve for x and y. So -1/2 in for t, 2 times -1/2 is 1. -1/2 squared minus 1, that's 1/4 minus 1, which is -3/4. So we're going to try our best here just to estimate here. -1, -3/4. So we see that the graph is moving to the right here because at t equals -1, it was here. At t equals -1/2, it's here. Right, so 0 in for t. I'm just going to go ahead and fill out the rest of the table here. We're just plugging in all these t values in for t and finding x and y. Okay, so next up, 0, -1. Using arrows here to indicate the movement of my graph. Next up, 1, -3/4. Next up, 2, 0. 3, 5/4. It's like 1.2. And then 4, 3. We can kind of see that this graph is basically kind of forming that parabola shape. Okay. I just want to show you that in the calculator, in our graphing calculator, we can also put it in parametric form and get this to show up. So in your graphing calculator, if you go to mode, you can choose parametric. So let me write that down here. So you can go to mode and then select parametric form. So I'm just fourth row down, I have function, parametric, polar, sequential. So I'm selecting PAR for parametric. If you go to y equals, it's going to now convert this in terms of t. So your x and y are now going to be defined in terms of t. So I'm going to type in my x equation, which is 2t. Now you can also type in, when we're used to clicking that for x, this will just convert to be t now that we're in parametric form. So 2t. And then under y, we can do t squared minus 1. And then under window, I'm just going to fill in the conditions that they have here. So minimum, we'll start at -1. Maximum, we'll go to 2. Step size, 0.2. So that means step size means that it's going to find a new t-value every 0.2 x min. Let's do -3.5. We're just trying to make it so that it'll fit with the window that we see here. X max, X scale, sorry, X scale is 1. Y min 4.5 and Y scale 1. Max 4.5. And hit graph. Let's see. Got T min -1, P max 2. So starting at -1, it's going to keep finding the next t value after steps 0.2. So if you hit graph, and so it's forming that graph that we see there. If we decrease the step, then it's going to find more order pairs at smaller increments of t value, and that's going to make the graph even smoother potentially. So if you do like 0.02 or something, it's going to find more points. Maybe take a slightly longer because it's finding more order pairs at shorter increments of t value. So we can also find a rectangular version of this without the t variable. So we can eliminate that t parameter through substitution. So given x equals 2t and y equals t squared minus 1, let me write those equations out. Find the rectangular equation by eliminating the parameter. So if we were to eliminate the t variable, we should be able to get it into something that we're probably going to be able to recognize a little bit easier. So we would like to eliminate the variable, eliminate the parameter. So like to solve for t. So which t variable would be easier to get by itself? Yeah, the x. Here you got to deal with square roots. It's a little bit messier here. So I'm going to focus on solving for t. And then we're just going to substitute. We're going to replace t with x over t, since we have a substitute for t in terms of x. So I'll replace t with x over 2. Do some cleanup. We get x squared over 4 minus 1, or y is equal to 1/4 x squared minus 1. So this feels a lot more familiar to us, right? We know that there's a y-intercept at -1. We know it's a parabola. It's going to be stretched 1/4, so it's going to end up looking like this graph. But a rectangular equation is not going to have the detail that a parametric equation has, because with a rectangular equation, we know where the points are, but we don't know when the graph is going to actually hit these points, right? And so a parametric is going to give you more detail. It's going to give you not only the shape, but it's also going to give you the path that the graph is taking on. So it just has additional information that rectangular would not have. Okay, number 3, same idea here. We're just trying to eliminate the t and trying to get this in terms of either just in terms of x and y. So with this one, we actually have an identity that we're going to see quite a bit here. And the identity of the one that you're most familiar with, sine squared x plus cosine squared x equals 1. So if I can solve for cosine of t and sine of t, I can make those substitutions. It says x here, but we could also say sine squared t plus cosine squared t equals 1. So if I solve for cosine of t, if I make that substitution, cosine can be replaced with x over 2 squared. Cosine gets replaced with x over 2, but we've got to square that. And if I clean this up, I can square. If I get rid of the denominator by multiplying everything through by 4, then we get something that we should be able to recognize. X squared plus y squared equals 4. This is basically an equation of a circle with a radius of 2. So a lot of times, parametric equation is going to give us more detail in terms of where the graph is starting, how the graph is getting formed. But if we get rid of the parameter, a lot of times it will get into an equation that we're more familiar with, a rectangular equation. Okay, so next page, we're going to move into the calculus portion, which is if an equation is given to you with that parameter t, we can find the derivative if we just think of it as different components that we need to include because of the parameter. So page 2. Okay, so page 2 here. Here's the formula for derivative involving parametric equation. So we know that derivative is just dy over dx. But if our x and y are defined in terms of t, then we can think of it as y prime of t divided by x prime of t. So in other words, we can find the derivative of the y component with respect to time, and then the x component with respect to time. So even though there is that parameter time, we can do a y component in terms of time, x component in terms of t. If we divide them by each other, we're able to get the full slope or full derivative for that parametric equation. Oh, and there's an additional condition that dx dt cannot be equal to 0, otherwise slope will be undefined. So given x and y are both showing us that third, that parametric variable time, t, we can still find the derivative by just finding the derivative of these separately and then just putting them over each other. So it's the derivative of the y component divided by the derivative of the x component. So I'm gonna, I know all I need is power rule, right? For y, I'm gonna just distribute that 1/4 through, so I don't have to deal with anything more complicated than power rule. So let me rewrite that y of t here. Okay, so we know that dy over dx is simply y prime of t divided by x prime of t. So y prime of t is simply derivative of my y equation, so just power rule in terms of t. So just be 2/4 t or 1/2 t. And then x prime, power rule here, t to the 1/2. And now we're just kind of trying to clean this up. We know the 1/2 will cancel out. Just have to merge the t's together. So t divided by t to the negative 1/2 is the same thing as multiplying by t to the 1/2. So add the exponents, 1 plus 1/2 is 3/2. So our derivative of this parametric equation is just t to 3/2. So as long as we know what the t value is, we can figure out the slope of this overall curve at any moment in time. All right, number 5. Given that x equals e to the t and y equals cosine of t, find the equation of the tangent line. So we're going to find order pair. If we plug in t in for within my parametric equation, I can find x and y. To find the slope, I can do y prime over x prime, plug in power over 2, and then point slope form. Okay, so there's our order pair, e to the pi comma 0. Now let's find the derivative. To find the derivative, we'll find y prime, x prime, and then divide them by each other. So let's find y prime and x prime first, before we plug in the time, before we plug in the t. So let's do this. Y prime. Just finding this component first. So y prime, cosine becomes negative sine. X prime, e to the u is e to the u times u prime. So we know our slope at t equals pi over 2 is just this divided by this with the pi over 2 inserted. So sine of pi over 2 is just 1. The negative is going to carry over. 2 and pi over 2 just becomes pi. So 2e to the pi. So we have everything that we need. We have our ordered pair. We have our slope. And now I'll just put it in the point slope form. Okay, we're just going to work through practice problems and just apply these concepts here. Okay, for the given parametric equation, eliminate the parameter, and that just means we have to find a way to remove t and get our equation down to in terms of x and y. So I'm going to solve for t with this x e to the negative t. I feel like there's less pieces here. I can solve for t by moving that negative t down, but if I want to move an exponent down, I have to involve natural log. Otherwise, we're just changing the value. So I'm going to use log differentiation to allow me to get that t to come down so I can solve for t. And if I can solve for t for one, I can plug in and eliminate the parameter by plugging into the other. So if we're choosing between which t to solve for, you usually just look at the equations and see, okay, which one will be the easier one to get t by itself. So I have a replacement for t, which is negative natural log of x. So I would like to get this a little bit cleaned up or clean up a little bit more. I want to take advantage of that e and natural log canceling out, but I can't quite do that until I can move this, basically this -2 to a different spot here. So I'm going to write it this way. Y is equal to e to the -2 natural log of x. And remember, within the log expression, any coefficient can be brought up as a in the exponent location. And now we have e and natural log, which is a nice clean relationship. We can drop those, cancel them out, and that x to the -2 will just come down. So we have y is equal to x to the -2 minus 1, which is a lot cleaner, or 1 over x squared minus 1. For number 2, find an expression for the slope. So let's just do y prime over x prime. We're just following this formula here. Okay, number 3, position is given by x and y. Find dy dx as a function of x. Let's find the derivative first. And then if the variable is still out of place, we can always convert them into the variable that we want. But we know it. We're just trying to get dy over dx for now. So y prime, power rule. So dy dx is just y prime over x prime. So we have our derivative in terms of t, but they want the derivative in terms of x. So let's find a replacement for t in terms of x. And make that substitution back into my derivative equation. And now I can replace this in for that. The square root and the square will cancel out nicely. So I'll be left with x minus 1 over 3, all divided by 3. Dividing by 3 is same thing as multiplying by 1/3. Oh wait, I'm sorry. My bad. The square doesn't and did not cancel out this square here. So sorry, the square root will have to stay. We're not going to be able to clean up as well as I thought we could. Right, so this is fine, or you can write it as 1/3 square root of x minus 1. A particle moves along the curve x, y plus y equals 9. We have dy dt and dx dt showing up. So this is basically trying to get us to use related rates, since time is the independent variable here. So related rates just means we're going to find the derivative of each variable, but then when we come across that variable, we have to attach a d over dt. So x times y, though, we have to go through what rule to find the derivative? Product rule, yeah. So f prime g plus f g prime. So x's derivative is just 1, and then dx dt. The function stays. F stays, and then g prime, y becomes dy dt. And here, y is by itself, y's derivative is 1 times dy dt. And then 9 goes to 0. Okay, so they're asking now to solve for dx dt. We have x that we can replace. We have dy dt we can replace. But there's one piece that we still need, though. We need to find that y value. How can I find this y value? Is there an equation that can help us find that y value that we need? Can we solve for y with the original equation? By plugging in what? 2, yeah. So you have a way to get to that order pair, even though they don't give us that full order pair. So 2 in for x. 2y plus y equals 9, 3y equals 9. Y is 3. Okay, so we have everything that we need. We have x equals 2, y equals 3, dy dt is 3, and then we should be able to isolate and solve for dx dt. Okay, next page. Actually, let me, I think these are all kind of very similar. Let me go to page 5. Let's do a extended problem here, parts A, B, and C. Okay, so consider the curve given by the parametric equation y equals t cubed minus 12t, x equals 1/2 t squared minus t. Find dy dx in terms of t, so we just find y prime, find x prime divided by each other. Part B, write an equation for the tangent line, so we can plug -1 here to get the order pair, plug -1 into the derivative to get our slope, point slope form. Then part C, we'll look at vertical and horizontal tangents. Okay, just power rule for y prime, power rule for x prime, and then just put them over each other. Okay, find the equation of tangent line. So -1 in for t to get our x value and our y value, -1 in for t to your derivative to get your slope, and then point slope form. Okay, any questions with A or B? Part C, find the x and y coordinates for each critical point and identify each point as having a vertical or horizontal tangent. So remember, horizontal vertical tangents comes from the derivative. So let me write dy dx from part A. Okay, do you guys remember where do we look for if we want to find horizontal tangent? Has to do with setting something equal to 0. Okay, it's going to be the numerator. Vertical tangent. Think of vertical tangent as undefined, right? So that's going to be setting the denominator equal of the derivative equal to 0. So let's do vertical tangent first, since they're asking for that. first. So vertical tangent will be when t is equal to what? 1, okay? And this says find the x and y coordinates. So how can I find the x and y coordinates if I know that t equals 1?
Okay.
Back, yeah, into the original, yep. We're just trying to find the order pair where the graph is going to experience that vertical tangent. So once we find that t value, it goes back into the original equation. Oh, I miss. This is y, and this is x. Yes.
Mom's here to pick them up.
Horizontal tangent. Set that equal to 0. So we actually have two different t values that can cause horizontal tangents. So we'll plug -2 into the original equation, 2 into the original equation. So we have 2 order pairs for horizontal tangent and 1 order pair for vertical tangent. So when I plug 2 into x and y, I got order pair 0, -16. If I plug when t is -2 into the other into x and y, I'm getting a different set of order pairs. Okay, last one here. Let's try number 16 on page 5. So build your derivative, y prime over x prime. Plug 1 in to the order pair. Or plug 1 in for t to get your order pair, plug 1 into the derivative to get your slope, and then point slope form. See if we can finish up number 16. Okay, so tonight's study for your quiz, tomorrow help session at 7:30. Your homework is pages 1 through 5. This will be due on Thursday though. Tomorrow you're taking the quiz. Thursday, I'll check pages 1 through 5, but I'll also send out a reminder tomorrow afternoon so that you know that I'll be checking these on Thursday.
Go enjoy your request.
I don't want to.
Huh?
I don't know if it's going like.
I really. Why would I?
Well, if you see infinity, you know it's in.
Oh, it's up.
I'll see a vertical interfering with the structure. Then you got to them and ask you to
What's your wife?
Yeah. This one, I think there's more. Yeah, so it's where you get. Here, if I play infinity, I'm gonna get. Walk in, 1 over 2b, which is here. Yes. But if you're, Q over 2, then you're gonna get infinity. If you get infinity, at any point, you stop saying.
Here's number.
Mark, thank you. Okay, thank you.
That was a good one.
I want to single business temperature. Yeah. We have a textbook page too. I'll never this one right here. This would be into two. Where that's how flexible it's just wasting from here. This. No. Yes, this is. Yes, that's a yes, and that will allow for L'Hopital's rule to be applied. Okay.
Thank you. Have a good day.
Have a good day.